Yesterday we looked at the goodness of fit. Today's test is the Homogeneity Test. Hope I'm saying that right. We're going to compare observed distributions. Alright, we already know how to test whether two proportions are the same. But now we have more than two groups. We want to test whether the students' choices are the same across all four of our colleges here, or our columns. The z-test for two proportions generalizes a chi-squared test of homogeneity. The goodness of fit test compares counts with a theoretical model, but here we're asking whether the distribution of choices is the same among different groups. The term homogeneity means things that are the same. So what we're going to test is, all of this data here, are they more or less the same? Or do we have differences in our distribution? When we look at the hypothesis tested, our assumptions are going to be the exact same. We're going to test the check the counted data condition, the independence, randomization, 10%, and the cell frequency. Remember this, we need to make sure our data is counted. And here, cell frequency, we need to make sure we have more than 5 counts per cell. There is one big change between this test and the goodness of fit, and that is how do we calculate the degrees of freedom. For here, the degrees of freedom is my number of rows minus 1 times my number of columns minus 1. So using this example, I have 4 columns. So that's 4 columns minus 1 times the number of rows, 3 minus 1. So that's 2 times 3. My degrees of freedom is 6. So please note this change. This is the big change here, other than how we calculate it, which is a huge change. So let's look at one example of doing our homogeneity test. We have reports from 4 colleges on the post-grad activities of their 2011 graduating classes. Are the distribution of students' choices of post-graduation activities the same across all colleges? So I have 4 different colleges here, agriculture, English, whatever these two are. And do those students after college pick employment, grad school, or something else? Please note how this is separated. My counting or observed values are going to be in this top row here. So all of these values. Note the ones without a decimal. Right? How do you count a decimal? You don't. And my expected values are below. Good news is you only have to enter the observed values when we test this in our calculator. The calculator will actually calculate the expected values for you. So all you need is the countable numbers, your observed. So what is our null and our alternative? Our null is that students' post-graduation activities are distributed in the same way for all 4 colleges, meaning they're equal in which they picked. Alternative is that they are not the same. Looking at conditions, do we have the counted data? Yep, these look countable. Again, no decimals. Independence, even though this isn't a random sample, students' plans should be largely independent from one another. Now we know that's probably not so much true. Students have friends. Hey, were you in grad school? You know what, I'm thinking about grad school too, and might convince them. But, let's not get that technical. Let's assume independence. And expected cell frequency condition. Are the expected values above or at least 5? These are definitely above 5. So we're good to go. Now, all right. How are we going to enter in this data, our observed data, in our calculator? Completely different. With these next 2 tests today and tomorrow, please pay attention. We're not going to go to stat edit because, as you note, stat edit, you're going to have one column with one set of variables here. Here we have 4 different columns, right? So what I need to create is a matrix of all this data. So let's bring up the calculator. So please demonstrate this with me. All right, you want to hit matrix here. See it's blue? So second x to the power of -1. you're going to go over to edit. Edit matrix A. I already have it in there because I've already worked on this, but edit matrix A. First thing you want to enter is the dimensions. It is a 3 by 4. So this is my rows, this is my columns. So type in 3 by 4. And make sure yours, I know I got software update, so. Once you have that in the matrix, now it's time to do our chi-square test based on this matrix. Note, I'm not worried about the expected because they'll give me that. So what we want to go to is stats, test, and where yesterday we went into the chi-squared goodness of fit, go one above. Chi-square test. Hit enter. Where did you put in your observed values? I put it in matrix A. Now note with matrix expected here, matrix B, it's going to put in that information for you. So you don't have to put in this information. This is just telling you I'm going to store the expected values inside of matrix B. Also, it's going to give you the degrees of freedom because it knows how to calculate rows and columns itself. So you don't have to enter that. All you have to do is enter in your observed values into that matrix and test. Bam. There's your chi value, 93.6. My degrees of freedom is 6. So note, I got a really large chi value based on my degree of freedom. And my p value is really, really, really small. Look how small it is. There's 18 zeros in between that. So would you reject the null or fail to reject the null?
Reject.
Yeah, reject, right? That's a lot smaller than 0.05. So basically, I reject the null. There's evidence that the post-graduation activities from these 4 colleges don't have the same distribution. And since this is so small, there's a lot of significance there. Now note, like I mentioned, it calculates that for you. Let's go back in our calculator and look at what it put in for matrix B. So if you go to second matrix, click on B, now you have this. That wasn't there before. Now you have a 3 by 4 matrix in there. Let's take a look at it. Bam. Notice how I did not enter that information, but it is exact same values as our calculator. So it is nice, yeah. Gives you your expected. Now, unfortunately, what it doesn't do that you have to do by hand is what's called the residuals. We kind of talked about this a little bit months ago. When we reject the null hypothesis, which we did, it's a good idea to examine the differences between the observed and the expected counts, called the residuals. Here's your formula. Take your observed, subtract from the expected, and then divide it by the square root of the expected. So I'm going to take, let's say, for example, my agricultural students who got employed. My observed is 209. I'm subtracting that from the expected, 2110.769, and then divide that by the square root of the expected. And I'll get this value right here, negative 0.12, let's just round 2. So what does that mean? The most extreme residuals, both positive and negative, attract our attention. It appears that ILR graduates are most likely to be employed. Meaning, who is most likely to be employed? Right here, right? That's the biggest number. Who's most likely to go to grad school? Which major is most likely to go to grad school? English, right? Largest number. Which is least likely to go to grad school? That's good. Agricultural. So see how you can read the residuals and how they can be effective? How they can help us out? Now you wouldn't do this if I failed to reject a null. Right? With my null hypothesis being there is no difference, then there's no point in calculating all this to see the difference. if you just said there isn't one. Does that make sense? And I can see here that others, or agriculture are most likely to do others. English are most likely to go to grad school. And A and S, does anybody know what this might stand for?
No.
No, I don't know. But they're most likely to either go to grad school or do something else. All right. So that is the homogeneity test. Notice the two differences between the goodness of fit. We have a difference of degrees of freedom, how to calculate that, but have no fear, as we just saw the calculator will calculate it for you. And the big difference is we need to enter in our information into a matrix and not into that stat edit.